In this video, we will discuss inverse functions. To illustrate the main idea, let's do a small example. Let f be a function from z5 to z5 given by f of a is equal to a minus 3 mod 5, and let g be a function from z5 to z5 given by g of a equals a plus 8 mod 5. Let's consider the composition g compose f. In blue, we show how each element in the domain of f is sent to its corresponding image under f, and in orange, we show how each element in the domain of g is sent to its corresponding image under g. Notice how each element on the left ends up being sent back to itself at the end of the composition. For example, the element 0 is sent to the element 2 under f, and then 2 is sent back to 0 under g. The function g seems to undo the function f, which we can represent by the arrows in purple. A function that undoes another function is known as an inverse function. Before we formally define the inverse function, we must make an important note. While we only showed the composition g compose f, the opposite composition, f compose g, must be valid and must also map every element to itself under the composition in order for a function to be considered an inverse. Now we can formally define the inverse. Let capital A and capital B be two non-empty sets. We say that a function f from A to B is invertible if, for every element little b in the set capital B, there is exactly one element little a in the set capital A, such that f of a equals b. The inverse of such an invertible function f is the function f inverse from b to a that assigns to each element little b in the set capital B the unique element little a in the set capital A, such that f of a equals b. In other words, the function f takes an element little a and sends it to its image, which is little b, while the inverse takes the element little b and sends it back to the element little a, where it came from. Before we do some examples, we need to discuss an important theorem related to properties of the inverse function. Suppose that f is a function from a to b, and that f inverse from b to a exists. Then the following are always true. Number 1, f is the inverse of f inverse. Essentially, this means that f and f inverse are inverses of each other in any direction. Number 2, f composed with f inverse is the identity function with respect to the set B. Number 3, f inverse composed with f is the identity function with respect to the set A. To illustrate the properties of this theorem, consider the following example. Let f be a function from the integers to the integers given by f of a equals a plus 2, and let g be a function from the integers to the integers given by g of a equals a minus 2. By substituting the definitions and algebraic expressions for g and f, we see that the composition g compose f yields the element a. Doing the same thing for the composition f compose g, we see that the end result is also a. Since these two compositions produce the same end result, g and f are inverses of each other. So we relabel g as f inverse. Let's do another example. Let capital E be the set of all elements x such that x is a natural number and x mod 2 equals 0. In other words, capital E contains all of the even natural numbers. Let f be a function from the natural numbers to the set E defined by f of a equals 2 times a. Does f inverse exist, and if so, what is it? To visualize how the function f works, we can list out the first few natural numbers, we'll use the first 5, and then compute their images. The function f sends the element 1 to 2, 2 to 4, 3 to 6, 4 to 8, and 5 to 10, continuing in this fashion. Essentially, the function f doubles the natural number used as input. To determine if f inverse exists, we need to figure out a way to send each of the images under f that are contained in the set E back to their unique preimage in the set of the natural numbers. As it turns out, this function f is invertible. Since all of the elements in the set E are even, by definition, this means that they are divisible by 2. Since the function f takes an element in the natural numbers and multiplies it by 2 to produce its image in E, if we define a function g from E to n, defined by g of a equals a divided by 2, we should be able to recover each of the preimages. If we consider the first 5 elements of the set E, which are 2, 4, 6, 8, and 10, when we apply our function g and divide each of these numbers by 2, we see that we do in fact recover the original preimages of these elements with respect to the function f. Visually, this confirms that our function g is f inverse. To confirm that g is f inverse mathematically, we substitute their definitions and algebraic expressions and perform the compositions g compose f and f compose g, which in this case both come out to equal the same value. So, g equals f inverse. As a non-example, consider the function f from the integers to the whole numbers given by f of a equals the absolute value of a. Notice that the only whole number with a single preimage is 0. In other words, the absolute value of both -1 and 1 is positive 1. The absolute value of both -2 and 2 is positive 2, and so on. Remember that for a function to be invertible, every image must have a unique preimage. Since 0 is the only element here that has a unique preimage, the function f of a equals the absolute value of a is not invertible, and therefore f inverse does not exist.